Bismillahirrahmanirrahim. Assalamu alaikum everyone. This is Mahanur Gul from Electrical Engineering Department, Sakkar IBA University. I'm doing my final year project on design of a series voltage sag compensator with reduced magnitude of transformer inrush current. Here in this video, I will discuss the working of series voltage sag compensator, and in the research how and why we aim to mitigate this transformer inrush current that is being generated while the voltage sags. A voltage sag compensator is basically a device that is used to compensate the voltage sags that are produced at the generation side due to any malfunction in the system. It comprises of an inverter, rectifier, bypass switches, and a series transformer. The bypass switches are used to bypass the series transformer while normal operating conditions. But as soon as sag occurs, the inverter is used to generate the compensated amount of voltage. The series transformer is here to add up this compensated amount of voltage with the utility line. In this way, a smooth voltage is being received at the load side. This transformer that also provides electrical isolation to the load from the grid itself comes with an inherent issue, that is transformer inrush current. To understand this concept, let us understand the working of transformer first. A transformer basically operates on the principle of electromagnetic induction in the form of mutual induction. Mutual induction is the process by which a coil of wire magnetically induces a voltage into another coil. The coil at the side from where transformer takes the power is called primary coil, while the coil at the side from where transformer delivers the power is called secondary coil. These two coils are not in electrical contact with each other, but are instead wrapped together around a common magnetic iron circuit called the core. This soft iron core is not solid but made up of individual laminations connected together to help reduce the core's losses. These two coils that are not electrically connected are magnetically connected through this core, allowing electrical power to be transferred from one coil to another. As the current starts flowing through the primary coil, a magnetic flux is generated in the core. When the magnetic lines of flux flow around the core, they pass through the turns of the secondary winding, causing a voltage to be induced in the secondary coil. The amount of induced will be determined by the Faraday's law that says induced voltage is equal to number of turns multiplied with the rate of change of flux. As we see here, the rate of change of flux is directly proportional with the voltage, or we can say that the flux is the integral of this voltage. In continuously operating transformer, the flux waveform and the induced voltage waveforms are shifted by 90 degrees, but a significant difference exists between the continuous mode operation and the energization of the transformer. This can be further demonstrated here. During the energization of a transformer, the voltage is at its 0 point, and the flux has also started at the 0. So, for a rising voltage just started from 0, the magnetic flux will reach approximately twice its normal peak as it integrates the area under the voltage waveform's first half cycle. This amount of flux, because of the non-linear characteristics of the magnetization curve, causes saturation of the transformer. As seen from the figure, exceeding flux from the knee point results in large magnetizing current that in some circumstances can be 10 times of the rated current in a transformer. We will not go through the mathematics behind this process. However, we must look through the factors affecting inrush current, that are transformer magnetic properties, operating time interval, and the sag depth. Transformer's magnetic saturation is responsible for the generation of inrush current in its windings. It stays as long as the compensator takes its time to operate. Higher the sag depth, lower the voltage magnitude. As equation P is equal to IV suggests that P is equal to I is equal to P upon V. Lower the voltage, higher will be the current at constant power. Therefore, sag depth is directly proportional to the inrush current. The amount of this inrush current is sometimes even higher than the rated current capacity. This inrush current damages transformer insulation current. Even sometimes stimulates over current protection, eventually fails the compensation. Due to this reason, many researchers are working to reduce or mitigate this inrush current. The common approach used by most of the researchers is controlling the inrush current while applying PWM techniques on the compensated voltage. Here the compensated voltage is injected at T is equal to T1. As the projected flux is reached at the maximum flux, you can see here at T is equal to T2, the risk of high inrush current is appeared. In this scheme, the original compensated voltage is cut off during the time T2 to T3. In this way, the flux does not reach at the maximum point and the inrush current is reduced. However, this technique successfully reduces the inrush current, but you can see here at the output waveform, the quality of the voltage at the output is being compromised. Due to this reason, this research proposes a series voltage sag compensator by using a current-controlled voltage source inverter instead of the conventional PWM inverter, using an enhanced PI control scheme implemented in a stationary frame of reference. Here's the MATLAB Simulink model for series voltage compensator. The earlier discussed simple mode block diagram has been implemented here. Simulink model diagram of a series voltage sag compensator is illustrated here. It consists of a compensator to generate the compensated magnitude to the load voltage. a series transformer to add up the compensated voltage to the grid line, and the thyristor switches to escape the series transformer for the period of regular grid operation. At the time when sag occurs at the grid side, the compensator generates the compensated voltage according to the sag detected by the controller. This magnitude of compensated voltage is added with the line voltage via series transformer. The current and voltage ripples of the inverter are filtered through the capacitor and leakage reactance of this transformer. In this manner, the load is supposed to have constant power supply. But when the compensator is on, the series transformer gets energized and an inrush current is generated in the transformer windings, as discussed in this figure. The amount of inrush current sometimes goes thrice the value of nominal current in the transformer. As illustrated in the figure above, a voltage occurs at 0.1 second and compensator starts it as the sag is detected. When the compensator starts injecting the compensating voltages, an inrush current due to the energizing of transformer is observed. The magnitude of this inrush current is around to 20% of the actual value. This is very huge amount of current, that is more than the design power ratings of the critical loads, hence damages the sensitive machinery. In this block diagram, the proposed system for series voltage sag compensator has been demonstrated. The double loop PI controller is used to set the high gains at given frequency for voltage as well as current regulation. Here the VLOD asterisk and ILOD asterisk are the three-phase feedback input current and voltage given to the controller respectively. These are compared with reference signal to calculate the error factor E of S. This calculated error factor is given to the PI controller. The PI controllers are tuned accordingly, where high gains for current regulation while low gains for voltage regulations are tuned finely. Finally, the controlled voltage generated from inverter is forwarded to the transformer, which is further added up with the lined voltage to compensate the voltage sag, hence providing smooth output to the load. This is the implemented current and voltage dual loop PI controller inside the compensator. You can see here, this is the error comparator, and these are the reference signals. The current and voltage feedback is being given from the load side. So this is a feedback loop actually, and these are the PI controllers in series, controlling the current as well as the voltage, and then the final control signal is being given out here to the from the compensator. So this diagram is basically implemented inside the synchronous frame of reference, but later this is the final implementation of the controller inside the compensator, The control technique is applied in a stationary frame of reference. All the synchronous techniques, frame of reference techniques have been implemented here, so no heavy transformations are used. Here this is the voltage feedback, and this is the current feedback. The voltage loop regulates the load voltage, feedback from load, and produces a reference signal for current control loop. These are three-phase voltage and current signals. So these are compared with actually three-phase AC reference signal to calculate error factor, that is in your phase, and then fed to the PI controller of the current control loop here. An average value model diagram of this system is this one. Although the PI tuning becomes a bit challenging because adjusting the PI gains with AC signals is quite critical. However, the implemented control strategy in this case gives satisfactory performance as that of the conventional sophisticated control techniques like DQ rotating. You can see the results here. The grid voltages that are not shown here at the utility side is producing 1 volt initially, but as soon as the sag occurs, that is at the T sag here, this is equal to 0.096 second. The utility voltage is reduced to the 0.7 pu. So the compensator detects the sag and it starts at T is equal to T sag. After a delay of T is equal to 0.004 seconds, this delay occurs due to the time required for the detection of fault and activation of bypass switches. Since the voltage at utility side has reduced to 0.7, so the compensator injects V compensate voltage of 0.3 pu as shown here. This is aided with the help of series transformer to the grid line to regulate the load voltage. These are the load waveforms for the system, V load and I load. Now this is the time where sag happened, and within this time period, 0.02 second, the sag has been compensated smoothly. So you don't see here any inrush current. It's not here anywhere. Hence the inrush current is decreased by 105% when compared to the conventional series voltage sag compensator. So this current control voltage sag inverter inside the voltage sag compensator has successfully mitigating the transformer inrush current. And also due to the whole algorithm is being taken inside the stationary frame of reference, so it has excluded all the need of additional heavy transformations. So this implementation is actually reducing the designing complexities as well. So far these are simulation based results, and for now, for the future work, we aim to generate the practical results and want to compare those results with this simulation and see the effects. So that's all about my presentation. Thank you.